All right, ladies and gentlemen. So what we're going to do today is we're going to talk about how to solve that formative 9.2, the one you guys took on Friday. So the first thing we're going to do is reread that problem. And it says that if the following reaction occurs and it occurs at 376 degrees Celsius, determine the Gibbs free energy. Then it says that ammonia, or NH3, decomposes into nitrogen and hydrogen gas. And then it gives us the point system for each of the points that we should be getting from this problem. If we take a look, we should underline a couple of key information. And the key information is our temperature and the reaction. It tells us that ammonia, NH3, yields or decomposes into nitrogen and hydrogen gas. We know that nitrogen and hydrogen are both diatomic elements, meaning that they both end up with two hydrogens or two nitrogens in a compound or in an element. They're bonded together. Now that we have that information, we need to balance the equation. So to balance our equation, we got to set up our T-table. Once we set up our T-table, we know we have nitrogen and hydrogen on both sides of the reaction. And we know that there's one nitrogen and three hydrogens on the reactant side. And there are two nitrogens and two hydrogens on the product side. In order to make this equation balanced, we first need to look and see if nitrogens are balanced. Right now we can see that the nitrogens are not balanced, so to balance them we have to change our reactant side, and we need to multiply it by 2 to have a total of 2 nitrogens on both sides. But in order for this to actually work, we need to take that 2 and put it as our coefficient in front of ammonia or NH3. When we do that, we multiply NH3 by 2, or we have two sets of NH3, which means we have two N's and we have twice as many H's. So we have to multiply our H's by 2 now to have a total of 6. If we look now, our nitrogens are in fact balanced, but our hydrogens are not balanced. So now what we have to do is balance our hydrogens. So we're going to multiply our hydrogens by 3 to have that total of 6. And you guessed it, we're going to put that 3 all the way up in front of our hydrogen. Now that we've done that, we have our balanced equation. Now we can figure out what else we need to do for this problem. So we know that we're solving for Gibbs free energy, so delta G. And we know that that equation is delta G equals delta H minus T delta S. Now if we're thinking about this, we don't have any of these variables except for T. So we need to first solve for our delta H and our delta S values. In order to solve for delta H, we are going to take the absorbed energy, or the energy absorbed when the bonds are broken between all of the reactants. So this is our reactant side. And we are going to subtract it from the released energy. That's the energy that we release when we form those new bonds, and that's when our product side. So it's really our reactants minus our products for that delta H value. You have to get these from your enthalpy. Remember, delta H is enthalpy. And you're going to get that from the enthalpy table that you're provided as extra resources, or that maybe you have on a different worksheet. Now our delta S value is a little bit different, because our delta S value, we are going to take our products this time and we are going to label those the S of the products, or SP, just for future reference. And we're going to subtract our products minus our reactants. So we're taking our reactants and subtracting them from the products this time, opposite of our delta H value. So we're also going to label that one SR for the reactants entropy value. So now that we know how to solve for our enthalpy and entropy values, we actually have to do that. So we have to determine which one we're going to do first. We're actually going to do our delta H value first, just because that's the one I've written down first. So when going to that delta H value, we're first going to look at our entropy table, and just to have that as our reference, it is placed at the top. And if we look at that, we also need to pay attention to the reaction once again. So let's rewrite our reaction of 2 ammonias yield or make 1 nitrogen gas and 3 moles of hydrogen gas. Now, if we're looking at that table, it shows the bonds between two elements. So we actually need to draw out our bonds or our compounds and elements. We need to draw out what they would look like or picture them in our head. So if we draw out that ammonia, we know that nitrogen is going to form 3 single bonds with 3 different hydrogens, because nitrogen is going to keep a lone pair, and then it will total up to 8 valence electrons around the nitrogen and 2 around each hydrogen, so they are all happy. Now, we know that there is 2 nitrogens, so we have to multiply that by 2, or you have twice as many of those nitrogen compounds. Now on our product side, we know that nitrogen by itself, when it's N2, actually makes a triple bond between those ends, so that each one can have a total of 8 valence electrons. And then we know that there are 3 hydrogens, and each one of those is going to be a single bond between the 2 hydrogen atoms. So between each of our hydrogens, there is a single bond, and there's 3 sets of that. Now that we know that, we can go ahead and start solving our problem. So if we are determining the absorbed side or our reactant side first, we're going to take our absorbed value, and it's going to be 6 times, because if we look at our nitrogen and our hydrogen bonds, there are 3 N bonded to H, single bonded to H bonds on ammonia, and there are 2 sets of ammonia, so there are a total of 6 NH bonds. So we have to multiply it by 6, and then if we look up on the table, we find out that the value is 391 kilojoules per mole. So now that we know that, there are no other reactants, so no other energy is being absorbed, which means that we just multiply our value by 6 to get the absorbed value of 2,346 kilojoules per mole on that reactant side. That's the energy being absorbed. Now if we take a look at the release side, so our product side, the energy that's being released, we first need to find the energy of an N triple bonded to another N. So if we look at our table, you'll actually see that the N triple bonded to an N is 941 kilojoules per mole. We then know that we have 3 sets of hydrogen single bonds. So we're going to take that and we're going to multiply it by 3. We find where our hydrogen bond is, and then we write down our value. So we find that on the table to be 436 kilojoules per mole. Now our next step is really just to multiply that 3 times 436 so that we can get this all out. So we're going to rewrite the 941 kilojoules per mole, and then we're going to add the new value, which is 1308 kilojoules per mole. Now, to find our total, we're just going to add those 2 values together. When we do that, we should get a released or a product side of 2,249 kilojoules per mole. Now, if we remember from that front side, or that first slide, we remember that the delta H is really equal to the absorbed minus the released energies, which means that we're going to take the 2,346 kilojoules per mole, and we're going to subtract the 2,249 kilojoules per mole. Once we do that, we will find our delta H value, and the delta H value is going to be positive 97 kilojoules per mole. Remembering that when we do our addition and subtraction for significant figures, we look at the decimal point to tell us where to stop our significant figures. And both of these have no decimal points, which means that we stop at the whole number. So there's 2 significant figures for our delta H value. Now, if we look at our delta H value, this isn't part of the question, but it will be something we need to know for that summative. If we look at that delta H value, we can determine endothermic versus exothermic. And we know that this has to be endothermic because there's more absorbed energy than there is released energy. So this reaction actually is absorbing the energy. In order for that reaction to happen, it's endothermic.